Okay, welcome back everyone. In this video we're going to take a look at the EKG lead systems. We're going to look at lead placement, and then we'll see about the different planes that are of information that are gathered here. So the first thing we want to do is we want to take a look at a little bit about theory of the EKG here. So we're going to take a second to do that. So EKG theory, and here we start. All right, so the EKG works under the premise that if you take two electrodes and you label each electrode, or you assign each electrode either a positive or a negative terminal, then if we have electricity that moves between these two electrodes, that we'll be able to tell which direction the electricity is moving in, and we'll also be able to determine precisely with multiple electrodes exactly the direction it's moving in. So we'll be able to say, yes, it's moving in the direction of positive. Yes, it's moving in the direction of positive, but not quite as much. Yes, it's moving in the direction of positive, but even less so, all the way up until a point where we get this 90 degrees from these electrodes and things start getting a little bit hairy there. So the concept here is, if we take an electrode and we assign it a negative status, and if electricity moves in the direction of a positive electrode, the resulting tracing is a positive deflection on the EKG. Now, conversely, if we take a positive electrode and we take a negative electrode and we allow electricity to move in the direction of the negative electrode, the result here is going to be a negative deflection on the EKG. So anytime you look at an EKG, if you see a positive deflection, and it doesn't matter the shape of the deflection, it can look like this, it can look like this, it doesn't really matter what the deflection looks like, as long as it's above neutral, meaning the isoelectric line, as long as it's in a positive direction, we're going to say that electricity moved in the direction of a positive electrode. Now, in a little while, we're going to tell you what those electrodes are, and we're going to actually name those electrodes so that you have an opportunity to better see exactly what it is and where it is on the body that this electricity is traveling in. All right, so similarly, if we have a movement of electricity, again, towards positive, a little less and less towards positive, the only thing that happens here is we'll still get a negative deflection, but it won't be quite as deep as this negative deflection. Last but not least, we might get something that looks like this for this guy here. All right, so let me draw those other guys in. Here we might have a positive deflection, looks like this. It's a little bit less than this one. And then for this guy here, it'll be even less. But it'll still be positive deflection. So all these that travel in the direction of positive, they'll get a positive deflection. Anything that moves away from positive or towards negative electrodes is going to produce a negative deflection on the EKG. So this is pretty much the theory of the EKG. It's really pretty simple. You put two electrodes, you assign them a negative and a positive terminal, and then you place them in very specific places on the body, and you determine the flow of electricity, the direction in which the electricity is traveling in, and that's going to tell us a lot about the normal rhythm of the heart, or the underlying rhythm of the heart. All right, so let's take a look at some of these leads now. So this is the theory behind the EKG. Now let's take a look at some of the leads. So let's take a look at the three main leads, and we'll say this is the 3-lead ECG. And we're going to look at these 3 leads specifically. All right, so the first lead you need to know. First, let's take a look at where we're going to put these leads. All right, so first lead we're going to associate with the right arm. Second lead we're going to associate with the left arm. And then the third lead I'm just going to put down here as the left leg, and I'm kind of putting it in the middle of the left arm and the right arm, and I'll tell you why in just a little while. All right, we're going to eliminate the right leg for now, because as I mentioned in class, the right leg kind of serves as a background eliminator of background noise. So it doesn't really play a huge role here in terms of these 3 leads we're going to talk about, other than to eliminate unnecessary electrical noise, if you will, on the EKG tracing. All right, so the first one you need to know about is this lead that's created between the right arm and the left arm, and this is known as lead 1. All right. Lead 1 is created between the right arm and the left arm, and in lead 1, the right arm is a negative electrode, and the left arm is a positive electrode. Now, you don't have to do anything specific for this other than to know that lead 1 is formed between the right arm and the left arm, and then when you plug your monitor in, it knows to assign the right arm or any information that comes from the right arm wire to a negative terminal, and any information that comes through a left arm to a positive terminal, and this is lead 1. And you'll see that lead 1 is actually a perfectly horizontal lead, which is going to play a role later in EKG interpretation. All right, so the next one we want to look at is the one that's created between the right arm and the left leg. All right, so this is going to be lead 2. And lead 2 is created between the right arm and the left leg, where the right arm is assigned a negative polarity or a value of negative, and the left leg assumes the positive pole of the lead. So lead 2 is formed between the right arm and the left leg, and in lead 2, the right arm is negative and the left leg is positive. All right, last but not least, we're going to finish off with this guy here, which is lead 3, and lead 3 is formed by 2 electrodes, one placed at the left arm, one placed at the left leg. This creates lead 3 for us. And in addition to that, the left arm in this case is assigned a negative pole, and the left leg is assigned a positive pole. Inside the machine, you actually don't have to do anything for this. It's done automatically for you. You just put the stickers on the right spot, and the machine takes care of doing with the data what it was programmed to do. So actually what you'll notice here is we have this triangular form that's taken shape, and this form or this shape is called Einthoven's triangle. And Einthoven's triangle plays a huge role in EKG interpretation because it allows us to establish a relationship between these 3 leads. Because triangles have geometric relationships, meaning that they have angles between them. So between lead 2 and lead 3, we know they're 60 degrees. We know that the same exists here, 60 degrees here, 60 degrees here. And we also know a little bit about the lengths or the distances that exist between these things. So there are some assumptions we're going to make on the EKG findings, or with the EKG findings, based on the fact that we've created a triangle, and triangles possess certain geometric properties. And that's why this theorem, Einthoven's theorem, says that if we take these guys, and if we were to add the values of lead 1 to lead 2 to lead 3, we'd actually get an answer of 0. So if you were to take the electrical information from lead 1, lead 2, and lead 3, and you add it all together, you should get an answer of 0. And I'll tell you more about what that means in just a little while. All right, so this is kind of important because this means that also if you were to do this, lead 1 plus lead 3, this would equal negative lead 2. So there are some relationships now that exist between this that we can geometrically and mathematically compute some different things. So actually, when you hook your EKG up, it is actually going to do some of these things to change the way some of the other leads look. In fact, we can create some leads, some other leads other than leads 1, 2, and 3 based on the geometric properties involved with a triangle and with using Einthoven's theorem. Now, the good thing is you don't have to do any of these calculations. These are things that the machine is going to compute all by itself. All right, what you need to do is put the 3 leads on in the right place, right arm, left leg, and put the right leg down at the on the wrists and ankles, of course, is where we're going to end up here. We'll talk about that in a second. And the rest of this is kind of created for you. All right, so there's this additional piece you need to know because, in fact, when you place these 4 stickers, right arm, left leg, right leg, you actually create a total of 6 leads. So the first 3 leads you create are leads 1, 2, and 3. But you're also going to create some additional leads, and these leads are called the Augmented Voltage Leads. And you'll see them as AV, and then there's going to be a letter after here. It'll be AVL, AVR, or AVF. So augmented voltage from the left, augmented voltage from the right, augmented voltage from the feet. So augmented voltage leads are actually created by using geometric properties associated with Einthoven's triangle, and actually these are calculated leads. They're not actually measured per se. All right, so let's take a look at how we get there. So the augmented voltage leads are created with Einthoven's triangle. All right, so let's take a look at these here. All right, so take this triangle, this is going to be the triangle that's created by placing electrodes on the right arm, and left leg. So this is this triangle that we start with. I'll also label the points here. This is left arm, this is left leg. We're not going to worry about this fourth. I'm going to call it a ground for lack of a better term for right now, but it's not really a ground. All right, so I want you to see that something magic happens here. Just as though you could use triangulation to find somebody in the woods by calling them out, calling their name out, and then when they respond to you, whoever's closest moves a little bit closer, and you keep moving in on the target or the noise until you find the person, you're going to actually be able to use this same concept here. So your machine is going to do this. It's going to say, I'm going to take the right arm and I'm going to leave it alone. The next thing I'm going to do is I'm going to take the left leg, the information from the left leg, and I'm going to add it to the information from the left arm. And in doing so, you actually bisect this leg of the triangle. So in other words, what you're doing here is you're creating this new thing that takes place, this new angle and this new lead that's in the green. And this point right here is established by the machine by taking the left leg's information and adding it to the left arm's information. And you'll see that you end up bisecting this data here. So you end up at this data point. You could also do left leg minus left arm. It doesn't matter because this thing's going to ultimately look at absolute values, or it's going to assign a negative pole to something so that these things essentially subtract from one another so that you end up at the midpoint. All right, so when your machine takes the right arm and holds it as a reference point, and then it adds the information from the left leg and the left arm, it creates a new lead, which is this lead in the green, and this lead in the green is called AVR, Augmented Voltage Right Side, right side. All right, and it does the same thing for the other one. So it can do the same thing for the left leg, where you'll see that it takes the left leg, the left arm, and to it, on the other end, it's going to create a new reference point between the right arm plus the left leg. This creates this new reference point right here. And then the same thing happens for this guy here, where the left leg becomes the primary reference point, left leg. And here it adds, the machine adds right arm plus left arm data, and now you get these new leads. So this lead over here is AVF, augmented voltage from the feet, lower leg towards the feet. This guy over here was AVL, augmented voltage, left side, left side. And you'll see now we've created 3 additional leads, and these 3 additional leads are leads AVR, AVL, and AVF. What you'll also notice we've created here is a triangulated new reference point, which is this intersection right here. And that intersection right there is called Wilson's central terminal. So Wilson's central terminal is going to play a big role here in just a little minute, because when we start looking at the precordial leads, those are leads V1 through V6, those guys are going to act a little bit differently, and they're going to use Wilson's central terminal as one of their reference points. All right, so let's take a look here. There are a couple things that have happened. Just to recap, we're going to look at the things initially. So this was Einthoven's triangle, and Einthoven's triangle allowed us to create 3 legs. This was lead 1, this was lead 2, this was lead 3. And the reference point here, right arm, left leg. Next thing we're going to look at are the AV leads. So this is Einthoven's. And from Einthoven's, we can actually derive something new, which are the augmented voltage leads. And the augmented voltage leads kind of look something like this. Here, here, and here. Where this is AVF, because it's at the feet. This is AVL, because it's on the left side. And this is AVR, because it's on the right side. So now we have these additional leads. And then we have this new reference point we talked about in the previous slide. We'll see that in a second. All right, so here's the demystifying. You put 4 stickers on, 4 electrodes. And the 4 electrodes are right arm, left leg, and right leg. And from those 4 electrodes, you get leads 1, you get lead 2, you get lead 3, and you get AVL, AVR, and AVF. So you get 6 leads from 4 electrodes. 6 leads, 6 different views, 4 electrodes. All right, So let's take a look at what should be happening here. So we're going to add another page and let's take a look. From the previous video, the one where we talked a little bit about the conduction system and normal depolarization and all that mess, I want you to appreciate that if you take your heart kind of sits sideways here in your chest. This is probably not a great picture here, but we'll make it work. Your heart depolarizes with a certain amplitude, meaning a certain amount, a certain energy amount, and a direction associated with that. So in physics, we call these things vectors. So vectors have a specific length, meaning that the arrow has a specific length, and it has a specific direction. So I'm just going to use this as a reference point just to show an angle, and I'm just going to say that it has a direction and it has a length. So vectors are are graphical representation of mathematical results. When you add certain things together, you can represent them with an arrow that has a specific length. You could assign a unit and a specific length to this, and they also have a very specific direction. Well, the heart has a lot of electrical stuff going on. So every time the heart depolarizes, it shoots off all these little vectors in different directions. All these little vectors are firing. Every little myocyte that fires is firing in certain direction. And it also fires with a certain amount of energy. So it's got all these little arrows here, and all these little arrows represent vectors. They represent vectors for each individual little myocyte that's depolarizing and then eventually contracting. Well, if you take all of these little red arrows and all of these little vectors from all of these little myocytes that have depolarized, you can actually add them all up and come up with a single answer, a single vector, which is an arrow, which will have a direction and a length. And if you do that for the heart, you'll essentially start with something like a reference point here, and you will have a vector that moves in this direction. So you're going to get this arrow, if you were to add up all the electrical information at once, that all the electricity that's being released, if you will, all the energy that's being released from the heart when it depolarizes, you would get a vector that kind of looks like this green arrow. So why do we care about that? Well, here's why. Because now what's missing from those previous graphs, we talked about all these things, Einthoven's triangle and the graphs here. Now we need to kind of look at how we can apply that clinically and what difference that makes for us. So while we're back on the screen, I want to talk for a moment about all of the polarity of these leads. And I want you to remember that the left leg was positive in both lead 2 and lead 3. I want you to think that the left arm was positive for lead 1 and it was negative for lead 3. And then I want you to remember that the right arm was negative for both leads 2 and lead 1. All right, so that was kind of that was something we mentioned on the very first slide. Now the AV leads are a little bit different. The AV leads don't have a negative pole. The AV leads are called unipolar leads or modified leads because actually their reference point is Wilson's central terminal, and the answer there is 0. There is no positive or negative. It's a 0 answer. AVR, always positive. AVL, always positive lead, and AVF, always a positive lead. All right, so let's go to the next slide here, and let's put all this together so that it makes some sort of sense. All right, first let's start with Wilson's central terminal. If you take Wilson's central terminal, and I'm sorry, I keep saying Wilson's, I mean Einthoven's triangle, and you again place the leads on top of this guy. And now you take a look at this vector that I've drawn, this green line. I want you to appreciate that the green line represents the vector of depolarization by the myocardium, and it kind of goes in this direction. So lead 2 most closely parallels depolarization vector of the heart, and that's why we use lead 2 to do our very initial training on dysrhythmia interpretation, because lead 2 most closely approximates the normal angle of depolarization of the heart, and therefore things that take place along this green arrow will best be represented in lead 2 since they're both going in the same direction. All right, so now let's again reassign our values here. Lead 2, positive down here, lead 3, positive down here, and lead 1, positive over here. Now we can start thinking about what our tracing should look like. So in lead 1, it would make sense for us in lead 1, if we have this green arrow, is it moving directly in the direction of lead 1's positive electrode? And the answer is no. But is it moving in the direction of the negative electrode? And the answer is definitely not. So it's kind of moving in the direction of positive, but it's not exactly moving in the direction of positive. So we're going to get a positive deflection, but it's not going to be super tall. All right, now let's go to lead 2. In lead 2, same question. Is this arrow moving directly in the direction of positive or away from positive? What direction is it moving in? Well, here we see it's very, very, very accurate. It is moving immediately in the direction of lead 2's positive electrode. So in lead 2, we expect to get a very tall deflection for depolarization when that shows up. Last but not least, look at lead 3. Remember that lead 3 is created by the left arm and the left leg, and in lead 3, the left leg is the positive electrode. So again, we're moving in the direction of positive here. So in lead 3, we can also expect to get a positive deflection. It won't be quite as tall as this one, but it'll be taller than lead 1. So if we look at these deflections, we should say to ourselves, hey, what deflection or what direction of deflection should we anticipate seeing on the EKG when we look at leads 1, 2, and 3? Answer is positive, positive, positive. Why positive? Because the deflection is directly related to the direction of electrical flow towards a positive electrode. And in the normal heart, we have the green arrow in that shape and in that direction. And as a result, we get a deflection that takes place, and it looks just like what you see on this little drawing here. All right, so this is the 3-lead Einthoven's triangle. This is the representation of what the main deflection should look like in all of these leads. They should all be positive, and now we've talked a little bit about why that's the case. All right, so now let's look at one more thing. We need to look at the AV lead. So let's look at, here's AVR, here's AVL, and here is AVF. I'll label those accordingly. They're all positive electrodes. And here's AVR. Now on top of that, I'm going to superimpose the deflection of depolarization of the heart in the green arrow. Now we should be able to, again, do the same thing that we did in the previous slide, and that is, what should the deflections look like in AVR, AVL, and AVF? Well, let's start with the easy ones. Look at AVF positive, AVL positive. This green arrow, it's not moving directly in the direction of either one of these leads, but it is moving in the direction of the positive terminal of the lead. And as a result, when we look at AVF, AVF should be a little guy, but it should be positive. AVL, little guy, but it should be positive. Reason for that is because this green arrow is moving in the direction of the positive electrode as opposed to moving up in the opposite direction. Now let's take a look at AVR here. AVR is this positive electrode here. We're going to call this the negative terminal over here, even though it's really a 0. This is Wilson's central terminal. And now this green arrow is doing this. So take a moment to think about what you think AVR should look like. If you want to pause the video, do that for a second. And now you should be able to say to yourself, well, hey, this green arrow is moving away from positive and towards negative. Therefore, I believe that AVR should look like this. And you would be absolutely correct. So AVL and AVF should both be upright. AVR should be a negatively deflected picture. And the reason for that is that normal depolarization is moving away from AVR. It's moving towards the negative terminal or the 0 terminal of AVR. And as a result, you get a negative deflection on the EKG. All right, so there's one more thing we got to talk about, and that is the difference between unipolar leads and bipolar leads. All right, so all the leads we've been talking about with respect to leads 1, 2, and 3, these are bipolar leads. A bipolar lead is a lead where you have a definite negative and positive pole. So leads 1 and 2 and 3 are bipolar leads because there's a definite minus and there's a definite plus. Unipolar lead, there is no negative end. There's a 0 end. And on the other end, there's a positive terminal. Right? It could be a negative, but in the case of EKGs, it's always positive. But a unipolar lead, one pole, has only one pole, just as the name implies. This one is a 0. So you can still have movement of electricity that happens like this, and you can still have movement of electricity that happens like this, as we see in AVR quite frequently. But at the end of the day, the zero here stands in the place of the negative electrode. It's just that electrically, it's not a negative terminal. It's a zero terminal. It has no value whatsoever. And so when we move in the direction of zero, we get a negative deflection. Or it's better to say, perhaps, if you move away from positive, you get a negative deflection. So unipolar leads are all of the other leads. So I'm going to hesitantly put the AV leads here because they're kind of unipolar, but they're a little bit modified. And then V1 through V6, these are all definitively unipolar. All right, so all of your chest leads, by the way, voltage 1, voltage 2, voltage 3, nothing too fancy here. The V leads go across the chest. These guys are all positive and they're all unipolar. And then 1, 2, and 3 leads, 1, 2, and 3 are bipolar leads in the system. All right, so we talked a little bit about lead placement here, and I'm going to just reiterate a couple important things. These things are called limb leads for a reason. They have to go on the limbs. So Einthoven's theorem says if you separate 2 points by infinity distance, then the result that you get to try to figure out the center of these points, remember that we're doing that for the AV lead. So here's Einthoven's triangle. In order for me to find lead AVF, which I've just drawn here, the Einthoven's theorem says that if I take this lead and I separate them by infinity distance, I am going to have the best chance at determining exactly what the midway point is between these 2 leads. In fact, he calls this midway point the electrical potential difference. So in order for us to calculate, or for the machine to calculate and then measure the electrical potential difference between the leads, right arm and left arm, they have to be put at infinity distance. Well, that's not possible because we don't have arms that long. So it's critical for us to put these things on the wrists and the ankles because, in fact, in order for us to get the right data for this midway point, we have to separate the leads by as much distance as we can. So the same goes for the lower extremities, and it's important for you to maintain an equal distance between top and bottom, because remember that in order for a triangle to have equal angles here, right, 60 degrees all around, it's got to have equal legs. So we're going to create equal legs by creating equal distance, wrists and ankles, between these electrodes. It's really, really important for us to do so. All right, so now let's see what happens when we don't. Let's say we take the wrists and we put them here. We're going to put the wrist leads on the shoulders instead. And then we're going to leave the ankle leads on the ankles. Let's take a look at what happens. So now we're going to get a triangle that looks a little bit different. We're going to get a triangle that looks something like this. And now when we go to calculate Wilson's central terminal, which is the reference point for those other leads, boy, I can't draw today. When we go to draw or to calculate Wilson's central terminal for those other leads, and those other leads being AVR, AVL, AVF, V1 through V6, you're going to notice that instead of being right in the center of this triangle, which is what we want, this point has moved up. And all that because we put the electrodes in the wrong place. So if we're going to move the electrodes to somewhere, anywhere other than the wrists and the ankles where they're equidistant from one another, and remember that even though these guys look like they're closer to one another, they're not really, because electricity has to come all the way back over here and travel all the way down here, which is actually the same distance as going from here to here. All right, so this distance is the same, meaning that this leg and this leg is going to be exactly the same here because we're about as tall as we are wingspan wide. All right, so it's important for you to keep these equal distance because otherwise we're going to artificially change this Wilson central terminal, and when we do that, we're going to alter the overall picture that we get on the EKG tracing. All right, so let's take a look at another possibility here. Other possibility is you got a below-the-knee amputation, or you have burns or trauma somewhere down here. You can't put the sticky down on the ankle. Well, if you move this ankle electrode up onto the thigh, then you must do the same thing for the left side. For the right side. And you must also do the same thing for the arms, because, again, we want to maintain this triangle that's that's equilateral. We want all sides to be the same. So this is also an acceptable placement, but better placement is the one we previously saw, wrists and ankles. So unless there's this ridiculously complicated reason why you can't put wrists and ankle electrodes down, then you should do so. And in the event that you can't, you should always move equally up towards the torso, the lower and upper extremity electrodes, so that they're equal distance from one another. Under no circumstance should these electrodes end up on the torso. Doing so really prevents you from getting a good Wilson central terminal out of this, and you end up having trouble with your tracing. All right, so we mentioned these in class. I just want to spend a few moments on it to reiterate some of the key points. Remember that essentially what you're doing here is you're creating a straight line, straight horizontal line between V1 and V2, and also between V4, 5, and 6, and then again between V2 and V4. So if you want to think about these angles, it should be one intercostal space difference only between where lead V2 and V4 exist. Only one intercostal space, not 2, not 6, not 7, because they're going to change the way your picture looks. So V1 goes just to the right of the patient's sternum at the 1, 2, 3, 4th intercostal space. V2 goes 1, 2, 3, 4th intercostal space just to the left of the sternum. The next one to go down, as you'll see here, is V4. Mid clavicle, 5th intercostal space. That's where V4 goes. Draw yourself a perfectly straight line. You don't want to put V3 down here. You don't want to put it up here. You put V3 right in line with 2 and 4, and you drop V3 down there. Next one to go is V6. This is the mid-axillary, all the way on the same line as where the armpit is. At the 5th intercostal space, you drop V6, and then again, draw yourself a perfectly straight line, and that's where V5 goes. We don't put V5 down here. We don't put it up here. It goes right in line with that V4 and V6. In some instances, we'll have to do a right-sided EKG, and essentially this is the mirror image of the left. You'll see V1 is here, V2 is here, and it kind of continues along, but the same exact rules apply. It's 4th intercostal space, 5th intercostal space, and then a perfectly straight line between V4 and V2 to put V3 down. All right. When you do a right-sided EKG, all of these leads are going to print out in the exact same way that they printed out for your left-sided tracing. Whenever you do a right-sided EKG, you should label them. Either just put a little R at the top, or you can put an R next to the lead that you moved. So for example, V4 normally resides right over here, mid-clavicle, 5th intercostal space. When we want to see what the right ventricle of an adult patient is doing, we will take this sticker, or we will take this electrode, we will put a new sticker on it, and we will then find the right mid-clavicle line and 5th intercostal space, and we will create this new lead, which we call V4R. And this is V4 on the right-hand side. V4R allows us to look at the right ventricle, and it creates a new lead. Again, when it prints out on your EKG paper, it's not going to print out V4R. It doesn't know where or what V4R is, so you're going to have to label V4R as V4R. All right, last but not least, I just want you to be familiar with the fact that if you take a straight line at the 5th intercostal space, you can create what's known as a posterior EKG. And the posterior EKG, as you can imagine, looks at the back wall of the heart. So V8 goes mid-scapular. V9 goes in a straight line between mid-scapular and the spine. And V7 goes between mid-axillary, where V6 was, and V8. Now, which ones do you use to do this? You take V4, V5, V6, or you can take V1, V2, V3. So I prefer taking V1 through V3 to make V7 through V9, and the reason for that is this. Think about the average girth of today's patients. They're kind of large. And so if you take 4, 5, and 6, sometimes these cables, since V1, V2, V3 are all the way on the other side of the front of the chest, sometimes V4, 5, and 6 simply won't reach to the back. So instead what you do is you take off V1 through V3, you leave 4, 5, and 6 in place, and now 4, 5, and 6 are closer to these guys, and these guys will always reach to the backside. We're going to talk about some different techniques and some different tricks so that you don't ever have to do a posterior EKG, but if you see it in the literature or if you see a tracing, I want you to have some idea of how to interpret it. All right, so we've talked about quite a bit of stuff here. We've talked about Einthoven's triangle and the importance of good limb lead placement. We've talked about the 3 leads that were created by Einthoven's triangle. Those were leads 1, 2, and 3. We also talked about the formation of an additional reference point called Wilson's central terminal. That was created also by the limb leads, and it served to create 3 additional leads called the augmented voltage leads. The augmented voltage leads we then labeled as AVR to the right side, AVL to the left, and AVF for the perfectly vertical lead that goes from the feet back to this reference point. We talked a little bit about bipolar and unipolar leads, and then we looked at what the EKG deflection direction should be based on what we knew about depolarization of the heart, and also based on what we knew a little bit about Einthoven's triangle. All right, so stay tuned for the next edition. We'll talk a little bit more about EKGs.